So, welcome back, and as ever, I do hope you and your family are keeping well. Right, so you hopefully know a lot now about reflection of light from my previous video. So what we're going to look at today, this can be a slightly shorter video, is the refraction of light. I've got to be really careful how I say those words and don't confuse them. Now, some teachers simplify this word refraction and refer to it as the bending of light. It's not quite the right term, but I think it'll help you understand it. Now, you know about this. You've seen it before. Have you ever put a straw into a drink or a glass of water and looked at it, and it kind of looks weird? It looks sort of broken or bent. And actually, if you look closely, the straw in the water actually looks wider, sort of magnified as well. Something weird going on, and that is caused by refraction. You may have noticed that when you stand in a swimming pool or water that's calm, sort of up to your waist, that you kind of look a little bit shorter. It doesn't do me any good. Okay, and that's also caused by refraction. And what's happening here is the light is changing direction because it goes through a different material. Okay, and light normally travels through air. Okay, and we consider it to travel through air very easily, to go at the speed of light, about 300 million meters per second. But when it goes through a different material, a different medium, like water or your drink, it slows down. It slows down a lot, okay, but it still ends up going at about 200,000 kilometers per second. Okay, so 200 million meters per second, okay, instead of 300 million. It's slowed down by going through a kind of denser, kind of thicker material. And it's this that causes refraction. So again, if you were here with me, what we'd do now is I'd stop talking, you'd be pleased to hear, and I'd send you off into the lab and we'd do an experiment to show light rays going through different materials, and we can't actually see it slowing down, but we can see it bending and changing direction. So I'm going to go into the lab now and do that experiment for you. So I've got my ray kit here and we've turned it on to produce one ray, and here's the glass block that we're going to use to put in front of the ray to see what happens. Okay, so if I put the glass block there, it's actually plastic, this one, but glass is what we normally used to use. Okay, then we've got the light going in, and it's actually going straight in and out the other side. A normal to the glass block would be 90 degrees, and we're shining light along the normal. But now let's turn the glass block, and you'll see what begins to happen. Okay, there's a couple of different bits of physics going on here. But what you'll notice is you get that bending effect again. The light goes in, bends towards the normal, and then comes out and bends again. The really important part here is that you can see that the light bends only when it enters the glass and only when it leaves it. It doesn't do any bending as it travels through. And the glass is more dense, so it slows light down. So we've got fast in air, slow in glass, fast in air, and what you're seeing at this surface and this surface here is that change in speed, and that's where the light refracts. But I don't want to pack this away without showing you what's happening here as well. Okay, that if you look at that, you're getting a reflection, and it obeys all the rules of reflection, that the normal is about there somewhere, and so the angle of incidence is equal to the angle of reflection. But we need to understand what's happening with these angles when we have refraction of light. So let's have a closer look at what we saw there with our experiment. So I took a glass block, and I'm going to draw that glass block now. And this is a little bit tricky. So here's the glass block. The ones in our lab are plastic. because we don't want students dropping them and cracking them. But when I was at school, it was always a glass block. So there we go. Okay. And we're going to sort of look down upon this. And what you've got to remember, of course, is this is air. The medium is air. Here's air. And all the way around the block. And the block itself, we'll call it glass. And I'll remind you that it's glass. Okay. Anyway, it's a denser medium to light. So if we shine a light ray straight into this along the normal, straight down, it clearly goes straight through. Okay. So we won't bother with that. But if we shine it in at an angle, this is the important bit. Okay. Don't forget how to measure that angle. So draw on the normal, remember. The light ray hits the surface 90 degrees. So here's the normal. Okay. And we have an angle here, and you know the name of that one. That's the incident angle. Okay. But we get some refraction now. So what happens is the light ray bends. Okay, and down it comes. And what you'll notice now is that this angle here is smaller. I'm going to give it the letter R as well. Okay, it's a different R this time, isn't it? This is the angle of incidence, and this is the angle of refraction. And they're not equal, are they? Okay, the angle of refraction here is less because the light slows down. Okay, so what happens when it leaves the glass? Glass, ray, normal. So you draw on the normal. And then you can see the small angle here. And what will happen is the light will change direction. And in this case, come out parallel, in fact. And off it goes. Okay, so let's look at this in a little bit more detail. Fast, 300 million meters per second. Slower, 200 million meters a second. Fast. Okay, so where does the refraction take place? When it hits the surface or changes medium. Okay, it only bends when there's a change in medium. Okay, where there's a speed change. So you now know about the angle of incidence and the angle of refraction. So what I'm going to do in a minute is look at this diagram in just a little bit more detail. Right, now this is complicated, I know, but we'll go through it a stage at a time. So you now know that we've got two angles that we're interested in. We've got the angle here of incidence. Okay, and we've got this new one here, and I'll bring an arrow out here, the angle of refraction. Okay, and you'll notice up there, it's a smaller number. Now, it's at this stage that things get a bit fiddly when I teach it, and I've spent years, literally years, trying to find a good way to explain this to students. Okay, thin material, air, thin, low density material. Glass, thick material, dense material. Okay, and there's a particular thing called optical density that the light feels. It feels it's going through thicker stuff. Okay, and there's a very simple rule. Okay, so that when light goes towards a denser material, you see I've written the word medium there, so it goes towards a denser medium, it bends towards the normal. Okay, so let's pull that phrase apart. So here it is. Okay, and look at that angle. It's far away from the normal. The light's going towards the more dense material. So as it goes towards the more dense material, it bends closer towards the normal. It's now closer to the normal. Now, I'm not going to write it down, but the reverse is true as well. Look at what happens when light goes away from the more dense. Instead of staying close to the normal, a small angle, it bends away from the normal. And this is true in every situation that you'll do. Whenever light goes towards a more dense material, it bends towards the normal, never onto it and never past it. Okay? And when it goes away from the more dense material, it bends away from the normal. Okay? At this stage, we don't need to do any maths on this at all. You just need to understand the diagram. Okay, so now let's look at another experiment we can do to show what happens when light hits glass and slows down. And this is light hitting a prism. Okay, so a prism is kind of, for us, a triangular shaped piece of glass. And this is a really famous experiment, and it's one that you probably all know about. Isaac Newton is famous for this one. And he was wondering what sunlight is made out of. So he was at Cambridge University, sitting in his room in Trinity College, and he had a hole in the blinds. I don't think he had curtains in those days, probably cloth was very expensive. So there was a hole in the blinds and light came streaming in, and he held a piece of glass in front of it that was this sort of shape, a prism, and the light that came in, I'll draw it with a black pen if I may, so there's the light coming in from the sun, okay, did something really interesting. That when it hit the glass, it slowed down, and if you draw all the correct normals and angles here, something really interesting happens. That the light splits into colours, and you get the red light bends towards the normal, and this is the tricky one, it then bends away from the normal, and down it goes. So there's the red. Green light did the same thing, but not quite. Green light bent towards the normal and then away from the normal. So that's green light. And finally, on my diagram, blue light. I'm overemphasizing it a bit here. Okay, did this sort of thing. Yep. And what he saw was a spectrum. Okay, a spectrum. Spectrum means, in this case, light ordered. Do you remember it's ordered in terms of its wavelength? That red is a long wave, green is a shorter one, and blue is a much shorter, or at least a little bit shorter wavelength. Okay, so what was Newton trying to prove? He was trying to prove, using refraction at this surface here and that surface there, that the light coming in from the sun that's very bright, and we'll call it white light. Okay, there we go, we have to use a black pen for that. White light, yeah, is actually made up of, and this is really weird, made up of colours. He suggests there were 7 of them. Yeah, red, orange, yellow, green, blue, indigo, violet. Okay, the spectrum, I've just drawn 3 here. And I think you're all familiar with this at the current period because of all the rainbows everyone's drawing for the NHS. I must say I've seen some of the rainbows that are completely the wrong way round and have got all the colours muddled up. But it doesn't matter. People are having a go. Okay, but this is the correct order. And it's the start of the way you can understand how rainbows form. It's not quite the way they form, but imagine that the prism is a drop of rain falling, and you can begin to understand that one of the processes that happens in a raindrop is refraction, splitting into the colours, and the other one, in fact, is a reflection off the back of the raindrop that makes sure that when you've got the sun behind you, the light hits it, refracts, and then reflects back at you. That's more complicated, but the main thing here is to see how a prism can cause refraction of light. Now, I'll just end by saying some scientists at the time said, but Mr. Newton, your prism has made colours. That's what it did. It made them. It manufactured them. He did something very, very clever. He put the prism in front of the colours, and guess what came out? It joined them all together. It refracted them in such a way that the three colours came out in one ray, okay, overlapping, and you saw white light. So he proved, using laws of refraction, that the light from the sun is a mixture of the colours that you've seen, okay, and the proof is if we put them on top of each other and mix them back up again, we go back to white light. So again, if you were with me in the classroom, and it'd be wonderful if you were, we get a prism out. I've got a high dispersion prism here, a really good one, small, but it works really well. And what we do is we get some bright sunlight through the gaps in the big curtains I've got, and we'd split it up into the coloured spectrum. And I normally turn it towards one of the boys or the girls' shirts or blouses, and we use that as the screen. And what's really cool is, you have to be careful with the intensity, is if you've got those colours coming in off the prism, you can move your eye across them. You need to be certain that you're not looking at really intense light, okay? And you can actually see the red, green, blue and the other colours as you move your eye across the spectrum. But shame you're not here, so what I'll do is I'll just quickly demonstrate that by blocking off the light from my projector and just leaving a slit, a gap like Newton had, and holding up the prism, and I'll show you the colours that we get. So if you look there, you'll see a lovely spectrum, and you see the colours of the rainbow and everything. Okay, so I've got a slit of light, and I'm passing it through the prism, and it's dispersing it into the colours of the rainbow. So let's now look at another use of refraction. And obviously we're not going to go around using prisms every day, but we do actually in a really weird way. The lenses in our eyes, or if any of you wear glasses, I'm getting old now, so I have to wear glasses to read. So I don't need them now for looking at the camera, but I do need them if I get my mark book out and I have to put them on and get close, etc. Okay, lenses, if you think about them, are just curved pieces of glass. That's kind of not a flat-sided, but it's, you know, when I say curved, I mean the sides aren't parallel. So what I'd like to do is to have a look at how lenses work quickly. And we're going to look at two types of lenses. And here you go. Can you guess the name of this one? Look at its shape. Okay. It's curved outwards. So this is a convex lens, and the one that goes with it, the other one, the concave lens. So what we're going to do is we're going to shine light at these, and again, I'm really sorry, I want you to do this experiment, but you're not here, so I will do it and demonstrate it for you. I'm going to take 3 light rays and shine it directly into the lenses, and let's see what happens. So 3, it's easier with parallel rays because it's easy to understand what's happening. Let's kick off with the middle one anyway. The middle one hits a flat surface, so it goes straight through. And here we go, there's that one. And there's that one. Again, anything in optics that we do is reversible, but I'm going to put arrows on and say that one, and that one, that one, that one, and that one. Okay. Let's now go into the lab, and I'll show you what happens when we shine rays into a convex lens and into a concave lens, and then we'll very quickly explain it and say what we can use these lenses for. So I've got my ray kit here. I'm just going to turn on 3 rays. So there we go. Okay, and I'm going to take the convex lens, so that's the one that curves outwards on both sides, and put it in front of the rays. And look what it does. I always like this one. So it refracts the light inwards and makes the rays cross at a single point, and we call that the focal point. So now let's do the experiment with a concave lens, and this is a biconcave. It's curved inwards on both sides. So I'll put that in front of the rays, and what you'll notice here is that the rays diverge. They spread outwards with a concave lens. It's interesting to think what might happen if I put the convex one in as well. Well, we'll have some bending outwards and some bending inwards. And if I push them together, if they both got the same power, but one bends outwards, a negative power, and one bends inwards, a positive power, we're back to where we started. Right, so we can now complete these diagrams knowing what happens. Okay, I won't go into too much detail, but we'll just do it a sort of simple way. So imagine this bit of the lens here is flat. So it's actually, the ray is coming in along the normal, so it goes straight through. Okay, so that ray is undeviated. It goes straight through. However, this one here, is not coming in along the normal, so it will bend towards the normal. It's quite complicated, and then away from the normal. And this one will bend towards the normal and then away from the normal. Hang on, do you see up there the little prism, the little triangle? Okay, so can you see this one coming along and bending down and down? Okay, a bit like that diagram. Again, complicated. So what most teachers do is, and it's not totally correct, is they draw the light coming into the middle of the lens and then just kind of bending down. Now you know that that's not quite right. The bending takes place here and here, but for simplicity's sake, what comes in, okay, and what do we get coming out? So there it is. There is the focal point of this lens. The focal point. Now again, I tend to go off on one, as I always do, because physics, there's so much to say. But this one converges rays. It brings the rays together. Okay? And we choose parallel rays. And if you choose parallel rays will converge at a single point we call the focal point. And from the middle of the lens to the focal point, you can measure with a ruler in meters, and we call that the focal length. Now, you can go on and on and on and on, because there are so many terms in geometric optics. The optical center, focal point, focal length. But the main thing is that you see that the light comes in and gets brought together. Even if the light came in a bit together already, it would be brought even more closely together. It always brings the light together if we set it up like this. What's it used for? Okay, well, you might have seen these as magnifying glasses. Okay. I'm tempted not to say boys here, but I kind of find myself saying that. Okay, getting this type of lens and holding it up in the sun and burning something. You shouldn't get up to that. Okay, because this is going to take the energy from the sun, particularly its infrared, and concentrate it. Okay, Lord of the Flies in that novel, where they use Piggy's sunglasses. Okay, to concentrate the light. Okay, so that's the convex lens. Let's have a look now at the concave. Well, the concave does exactly the opposite. Again, it bends or refracts the light at each surface, but I will just draw it happening like a lot of teachers do, just in the middle of the lens to keep it simple. So that ray goes out and that goes out. So the concave lens diverges light. Okay, it causes light to spread out. And focal point, it does have one actually. It has a secret one. Do you remember the word virtual? Not where light doesn't actually come from. We had that in the mirrors. Okay, if you were to follow this ray back, and to imagine that ray going back to there. From here, the optical centre, to there, is the focal length of this lens. Plus, minus. This is a minus lens. Okay? And I hope now you think a bit more about lenses when you go to the optician, because these are what they drop in the glasses in front of you to find out whether your eyesight's okay. And if you're someone who's short-sighted, okay, your eyes are too strong for various technical reasons, okay? So you need to put in front of it, even if it doesn't look like it, you need to put concave lenses to bend the light out a bit, and then your strong eye will bring it back into an image, okay? And you will have a prescription that's minus some diopters, maybe minus 1.7 diopters, a measurement of the strength of the lens, and that it's concave minus. And if you're long-sighted, so you can see a long way away, but you can't see close up, okay? If that's the case, you will use convex lenses. Shall we say your eyes aren't strong enough? So in comes the light from the page, and you need a lens to help you get it together first, and then your eye does the rest. Okay, so again, me going off on a bit of complex stuff there, but what you need to know is that curved pieces of glass will refract light, and convex will bring the light inwards more, and concave will push the light or refract the light out further. So I do hope you found that lesson interesting, and you now know quite a bit more about the refraction of light. You understand about the incident and the refracted angle, and bending towards the normal when light goes towards a more dense material, and bending away from the normal when the light goes away and speeds up away from a more dense material. Anyway, you're now experts, I hope, if you've seen both my video lessons on light. So I'll be doing other lessons soon, and I look forward to seeing you then.